Welcome. We are at a day in our schedule that is designated as a review/flex day. I did take a sick day last week, but I don't think we have much to catch up on. We're pretty much on top of things because we just talked about computing volumes with cylindrical shells. So I think that makes today mainly for review. What are we reviewing for? Quiz B. Quiz B, your second quiz of the semester, will be tomorrow. Let's talk about what's going to be on that quiz. Pull up my whiteboard here. Right. Quiz B, in class on 2/8/23, which is tomorrow. There we go. What are we going to be doing? We're going to be doing mainly the stuff we've been doing lately. Area between curves. 2.1. Volumes of solids with predictable cross sections, or consistent maybe is a better word than predictable. That was in 2.2. And then volumes of solids of revolution using washers and or disks. That was 2.2 and 2.3. So there are some things that are going to be on the quiz. I think that might be pretty much it. The other stuff we've been doing lately is, since our last quiz, would include techniques of integration. So things like trig substitution, partial fraction decomposition, and then integrating numerical integration. If that stuff, I don't think I'm going to put any numerical integration on this upcoming quiz. If we want to do any trig substitution, that sort of thing, then I would maybe incorporate that into an area question, right? So maybe I would give you a function to find the area under or between two functions or something. And one of the integrals requires a trig substitution, right? So if I was going to put that on there, I'd put maybe one of those on there, one tricky integral that requires something new, like a trig sub or a partial fraction decomposition. But that's about it. I wouldn't do much more because we don't have a ton of time. So I'm thinking this might be, last time I gave you guys 30 minutes for the quiz. This time I might do either 40 minutes or maybe the entire 50 minutes. Just because some of these problems can be kind of tricky. If we have extra time, then besides the if we have extra time after the quiz, what I would want to do is maybe start on section 2.4. Maybe. But we have a whole day dedicated to 2.4, so I don't think we really need to. So I think we might as well just take the full 50 minutes for this quiz. So I'll go ahead and make that decision right now. You will have the full 50 minutes. We don't really need that time for the next topic, so might as well put it to the quiz. And if you finish early, you finish early, and then you get to go and, chill out before your next class. Maybe some trig sub or partial fractions involved in the integrals. Must integrate by hand, must solve integrals by hand, but may check with Desmos or calculator. Okay. So for the quiz, I want full handwritten solutions, but I do, because that's part of it here. We have been studying that as well, right? But yeah, you'll have Desmos available. Okay. So that's what's going to be on the quiz. Do you guys have any questions? Okay. Great questions. There's some formulas to memorize. Yes. So like before, you will get the you get trig identities and Calc1 differentiation/integration formulas. But I do want you to memorize the new stuff. So in particular, you might want to memorize the formulas for integrating with for volumes of revolution using washers and shells. So I did post something a little while back, but I didn't tell you. I just very sneakily posted something in here in general documents. Outline review and formulas. So this is a document I put together when I was teaching this class over the summer, last summer. They said, can we have a review? And I said, yeah, I'll put together sort of a review. This was in preparation for the final exam. Got a bunch of formulas on it. So you can use this to study. You won't be allowed to use this document during the quiz. This would be a study tool. Okay. So, like, what do you use? What sort of trig substitution do you use? Right. How do you set up partial fractions? Well, it depends on the context, right? If you have an irreducible quadratic factor, right? If you have linear factors, if you have a repeated linear factor, right? That sort of thing. We haven't gotten to improper integrals yet, so don't worry about that. The stuff we've been doing and the stuff that's going to be on this quiz is mainly, what falls under unit 2 here. I haven't been organizing this class into units quite as explicitly as I did when I taught it over the summer. But unit 2 is like chapter 2. It's the chapter we're in right now. The units are just the chapters. I just rearranged them a little bit. Yeah, area between curves, top function minus bottom function, that kind of thing. But then that's vertical. That's dx. You could flip this around and make it horizontal as well. It would be slightly different. Volumes of solids with predictable cross sections. If A of x is the cross-sectional area, then the volume is the integral of A of x. That's kind of easy. But then, you got the disk method and the washer method and the shell method. So disk, washers, shells. Disk is just like a special case of washers where the inner washer is radius 0. So it's like disks are just like the same as washers, except you just don't subtract something out of the middle. You just pick the outer disk and that's it. So that's why it's just an f of x squared. It's not like a difference of squares. Now, I kind of wrote the different versions if you're revolving about the x-axis versus if you're revolving about the y-axis here and here. This formula sheet does not say anything about what to do if you revolve about an axis other than the x-axis or the y-axis. So we could review that today, because I did teach you that. That could be on the quiz. And that's as far as we've gotten. So you don't need to worry about this stuff. That's going to be tomorrow, or that'll be Thursday rather. And then this stuff too. And this goes till the end of the semester, so it's got tons of cool stuff in it. So we can keep coming back to this document as we move forward. But anyway, so that's there. Okay, so for now, let's kind of nab this stuff, which is the main stuff you want to focus on. Let's put it over here in the notes for today. So I think how many questions are on the quiz? I don't know yet, but I'm going to aim for like 3 or 4. No more than 3 or 4. If you're wondering about exercise set 2, I still have to give you, exercise set 3, which you guys turned in on Friday. I still have to give you feedback on that. The plan was to do it over the weekend, but that plan did not fall through. I'm catching up from my sick days that I've had recently. But yeah, I'm gonna do my absolute best to get you guys feedback on exercise set 3 today, so that you have that feedback before your quiz tomorrow. Do my best. Do my best for you. Might be a late night. We'll see. But yeah. So I was wondering if you guys want to go over an example. I have an example that I kind of quietly put on the board yesterday, and a couple of you worked on it. But I thought we could go over it together. That sound good? Right. So this example comes from the simple idea that one of the common shapes, one sort of common shape you get from a solid of revolution is like a donut. Okay. Let me see if I can draw a donut here. Not a great picture of a donut. It's pretty good. This would come around like this, all right? And then you've got this hole in the middle, right? It's a donut. It's shaped like that, right? It's basically what you get by taking a circle and revolving it around an axis. Here's our axis of revolution, right? So let's look at an example of a circle. Now, how do you describe a circle? Let's keep our circle centered at the origin, so we can keep it nice and simple. And let's say that the radius of this circle is 3. There's our circle centered at the origin. The circle is like x squared plus y squared equals radius squared, right? Equals 9. But if we want to integrate this, I mean, it's starting from something like that is kind of hard because you want it, well, you're going to integrate it. You need a function. So you got to solve for x or you got to solve for y, depending on like what strategy you're going to use. Let's say we're going to revolve this around the axis x equals 5. Okay, so then the other half of your, the other circle would be here, and here we are revolving around there, around that axis. Okay, to make our donut. And so on. Now, there's a couple different approaches to this. We could try to set it up where we slice this direction and revolve around like this and do shells. Okay, we could do shells, or we could slice it the other way, slice it like this way and revolve it around like that and do washers. So, how would you like to do it? Any preference? Maybe we could set up both and see which integral looks easier to solve. Let's start with I guess we'll start with washers. So if we're going to do washers, we're going to have to set up a dy integral, right? This is similar to revolving about the y-axis. The line x equals 5 is parallel to the y-axis. So what I taught you about how this matches the name of the axis that you're revolving around, that would like apply in this situation, right? This is parallel to the y-axis, so we're doing a dy integral. It's confusing because the way that you label a vertical line parallel to the y-axis is by stating what the x value is, like x equals 5. Like you describe the y-axis by writing x equals 0. So it gets kind of confusing when you're trying to like, does it match the axis or not? If you draw a picture, it's obvious, because if you draw a picture, it's like, okay, so each washer corresponds to a y value, right? And all the different washers, or each washer is going to be determined by which y value you're looking at, right? It's the washers don't go this way. The washers go clearly, this direction, corresponding to the y's. So anyway, it's going to be a dy. Our limits of integration, therefore, need to be y values. This is being a circle of radius 3 here. We're going to go -3 to 3. We might be able to sort of cut this in half and just do like part of it, but let's not worry about that for now. Because there is symmetry. We could cut the donut. We could cut the donut in half this way, like a bagel. I don't know why no one ever cuts a donut in half, because it's, unless actually there was I used to live in Dayton. Was it Dayton? No, I used to live in, well, I did used to live in Dayton, Ohio, but actually I'm thinking of a restaurant in Lansing, Michigan, which served a cheeseburger on a donut instead of a bun. Anyway, so I guess there might be some rare occasions where you'd want to cut a donut in half the long way. But anyway, so we could cut it in half and then do like 2 times the integral, whatever. Let's not worry too much about that. Indeed. I couldn't eat it, but my wife tried it, and I couldn't eat it because I have celiac disease, so I got to stay gluten-free. But my wife tried it and said it was not bad. It was an experience. She said she would probably not order it again. Anyway. All right, so we need to do our like pi r squared, basically, but we got to do like big R squared minus little r squared here. Right, because we're just doing like integrating the circles, right? The area of the cross sections. Difference between big circle and little circle. So we're going to need to solve this equation for y. Oh no, for x. We got to solve it for x and get it as a function of y, right? So if we do that, we can do y squared is 9 minus x squared, and then y is either plus or minus the square root of 9 minus x squared, right? So this plus or minus is kind of important. The plus corresponds to one side of the circle. And the minus corresponds to the other side of the circle. Okay. Now, how are we going to do this with like revolving about this axis x equals 5? It's a little bit tricky to see exactly how it works, but you can do some reasoning with this picture here. Okay. That's our outer radius, capital R, right? The outer radius is going to be 5 plus some more. And the amount more, right? This distance is 5, and then plus a little more. And the amount more that you add on beyond 5 is basically the absolute value. It's like the opposite of those negative numbers over there. Those negative x values. Oh, crap. I just realized I made a mistake. Can anyone see the mistake I made? I even said it the right way, and then I did it the wrong way. Yeah, thanks, Wes. Yeah, Wes has got it there. It's Jonathan. In the chat, I said the right thing over here, and then I just did the wrong thing. So we actually wanted to solve this for x as a function of y. So it's pretty easy because you just flop them around. It's because it's symmetrical. But there we go. So I've fixed that now. Yeah, so I think what we want to use for capital R is like 5, this distance, plus the opposite of our negative square root, right? So it's actually plus the square root. 9 minus y squared. And then for little r, we're going to do the 5 minus some amount that comes from this side over here. So 5 minus the positive square root. So 5 minus square root of 9 minus x squared, y squared. There we go. How's that? Does that look okay? So the square root of 9 minus y squared. I'm not sure what your question is, Ibrahim. Can you expand on that? So the reason we're using the square root of 9 minus y squared is because we're working with this circle, right? Which has the equation x squared plus y squared equals 9. But then we need to describe that circle using functions. And since we are setting up a dy integral, we want our basically our x values as functions of y. So we solved for x. And this square root of 9 minus y squared, that would then be telling us the x values for different y inputs. So x's for different y's. That's the negative square root. And then on this side, we have the positive square root. Different x values for different y inputs. I'm not sure what else to say. Salman has a good question. How do you know which one to put for big R and which one to put for little r? In general, if you draw a picture, it can help because here you can say, all right, which one is farther away? If I do like, which one is going to give me bigger numbers? That's the big R, right? That's the bigger value. It's the larger radius. So 5 plus square root of 9 minus y squared is giving me larger numbers. And 5 minus the square root of 9 minus y squared is going to give me smaller numbers. Okay, they're all going to be positive numbers because the biggest you could possibly get with the square root of 9 minus y squared is 3. This function never gets bigger than 3. So we're never going to be adding or subtracting more than 3. But the bigger ones are the larger radius and the smaller ones are the smaller radius. So it's really that simple. It's just that's how you tell which one. And then the other thing is if you get it wrong, it's not going to be a big deal because it's just going to be the subtraction will be in the wrong order. And then it'll be negative instead of positive, but that's an easy fix. Okay. So yeah. Now putting these in here, we get a fairly yucky integral. Now it might simplify a little bit. We get like 5 squared is 25. We get plus 10 square root 9 minus y squared plus 9 minus y squared when you square the square root. That minus this stuff over here, 5 squared is 25. You get 5 times negative 2 times the a, b, so these are opposites. So you get like minus 2ab, which is with another minus here is going to be a plus 2ab. So we have plus 10 root 9 minus y squared. And then squaring this, you have negative times negative is going to be positive square root squared. So you have another positive 9 minus y squared, but then you're subtracting it. So minus 9 minus y squared. So it looks super yucky until you expand those and the 25s cancel and the 9 minus y squareds cancel. And we really just get 10 plus 10 is 20. So what we're integrating here is really just, let me give myself some more space. What we're integrating here is really just 20 pi times the square root of 9 minus y squared dy. So that is a simplified version of that integral that we get after expanding and just canceling terms that cancel out from the squares. Okay, so let's stop at that point, and that seems like an integral we could solve. What strategy would you use to solve this? This is going to be a trig substitution. Yeah. 3 sine x, correct. Mm-hmm. Okay, let's try setting it up with washers instead of shells and see what the result is. Okay. With washers, we're going to want to do the opposite. So for washers, we're going to, instead of solving for x, we're going to want to solve for y. So we get the same functions, but just with the x's and the y's swapped. Okay, so now this represents, instead of the left and right sides of the circle, this represents the like top and bottom of the circle. Okay, so the minus is the bottom half here. Oops, sorry. And the plus is the top half, this circle. Okay, and we're revolving about the same line, the x equals 5. Okay, but now what I want to do is take slices in this direction, right? And revolve them around to make my shells. So we are going to want to do, and I'll kind of bring it over here. We're going to want to do an integral with dx this time. Okay. So the shells, each individual shell corresponds to an x value, right? And we're going to do shells all the way across. So Again, so this time we would take the range in x values for the limits of integration. It's the same because it's a circle. So we're still doing -3 to 3 on the x values there. And then what we're going to want to do is use our shell formula, which is 2 pi times the radius of the shells. And the radius of the shells, this used to be 2 pi x if you're just revolving about like the y-axis, because the x value is the radius. It's the distance away from the y-axis. But what we want to do is replace that with the distance away from 5, right? We want to replace it with the distance away from our axis of revolution. So if this is your x value here, what is this distance? Here, I'll draw it down here. Here we go. Cheyenne puts out 5 minus x. It's the distance between 2 points on the x-axis. It's the distance between 5 and x. You can just do final minus initial, right minus left. So 5 minus x. Perfect. Yeah, so that radius is 5 minus x. And then what we want is to, of course, do 2 pi r times the height, right? Which is our sort of f of x minus g of x, right? And so that is going to be top curve minus bottom curve. And when we do top minus bottom, what we get is the positive square root of 9 minus x squared minus the negative square root of 9 minus x squared. So this was minus negative, gives us plus, right? So so actually what we get is 2 times that square root, which makes sense because it's kind of like the top half and the bottom half are both equal to like the distance square root of 9 minus x squared. So it's double, right? So that's 2 of those. So what we actually have here is 4 pi times 5 minus x times the square root of 9 minus x squared. -3 to 3. Now, probably you're going to want to like split that into 2 pieces. And I'm actually a little bit confused about why. Huh. Okay, I'm a little bit confused, but we'll see. Maybe it's going to be fine. 4 pi can distribute across here, and so can this, right? You can kind of distribute this across and get like 2 integrals out of that. So one of those integrals is going to be 4 pi times 5, 20 pi, times this square root, 9 minus x squared, dx. And the other integral is going to be 4 pi times x times that square root of 9 minus x squared. 4 pi x square root 9 minus x squared. And we have this. You see why I'm confused? Does anyone see it? What's wrong?
Our first half of the new equation looks the same as the washer equation.
Yeah. And so what's up with this part? Oops, sorry. What's up with that? We're subtracting something. It's like they're the same, except one of them has subtracting something and the other one doesn't. So that's a bit concerning. I hope that function's integral from -3 to 3 is equal to 0. If it's not equal to 0, then that seems a little weird. Let's check. Oh, sorry. So first of all, though, I would say from the perspective of like solving these integrals, like the strategy you would use to solve these integrals, I think they are sort of comparable in terms of difficulty, because this one also is going to require a trig substitution here. How could you solve this integral, though? It looks a lot like it might be also a trig substitution. And I believe you could do it with a trig substitution, but there's an easier way. Okay. Thanks, Cheyenne. I'm glad it's 0. Okay. But yeah, this is a U sub. Thanks, Isa. Yeah, this is a U substitution. You can just do U equals 9 minus x squared on that one. And the reason that's going to work out nicely is because of this x over here. Yeah, because of that x. You don't need a trig substitution for that. Just do a U sub instead. So yeah, there's two approaches to finding the volume of the donut. I forgot to label this one. That was washers. This over here was shells. So there we go. We got the same answer. Strangely enough, one of them was 2 integrals, the other one was 1 integral, and the second integral, as Cheyenne confirmed for us, is equal to 0. So it's a bit odd if that shows up, but it does. Okay, what else should we do? What else do you guys want to review? If we're going to do anything, it's probably not going to be on a new page. So while you think about that question, I'll go and export this. Okay. Volumes with cross sections. Excellent. So let's pick a sort of a region. Let's get really wacky. Let's do something with like a sine function. And then like x plus 2 or whatever. And then we'll do x equals 0 and x equals pi. There we go. And then I want to shade the region we want. We're going to do everything that's between sine and x plus 2. There we go. But only on this interval between 0 and pi. Right, there we go. So that's going to be our region. We'll pick that as our region. Okay, so that's a region in the x-axis, in the xy, like the xy plane, basically. So what I want to do is rotate that a couple of times and skew it. Is that how I skew it? I feel like I messed that up. I want to skew it. Yeah, like that. And then rotate. There we go. That'll be fine. Oh, yikes. Sorry, I keep messing this up. Skew it. Rotate, rotate. Great. Okay, so now got our x-axis down here, our y-axis over here. We have this sort of two-dimensional plane, two-dimensional region. And now we can say that we're going to like build a solid by putting some sort of shape on top of here. Let's do like triangles. I'll just put myself on a new layer here and and pick a nice color, pink. Do triangles this direction. Let's do 45, 45, 90 triangles in that direction, like that. Okay. So there's our three-dimensional solid thing. Okay. This is one of two ways that I like to approach building a problem like this. It's decide what the region in the XY plane is, and then decide what shape the cross sections are, and then that produces some sort of shape. And this isn't actually going to be a straight line. This is going to have to be a curve like that. There we go. That looks better. The other way is to think about the three-dimensional shape to start with, and then figure out how are you going to slice it to produce cross sections. That would be like, remember when we did the pyramid and we were like, how are we going to cross, how are we going to slice the pyramid in a way that has like consistent cross sections all the way through? That would be starting with the three-dimensional thing and figuring out how you're going to slice it. Versus this is like deciding what the slices are and then letting that sort of determine the shape of the three-dimensional thing. Anyway. So in this case, all of our slices are these, triangles like that. So we can think about how we're going to integrate this to find the volume. What do you think, folks? How should we find the volume? Let's go step by step. First, dx or dy? Dx. Every one of these cross sections corresponds to an x value. That's the direction, we're slicing it perpendicular to the x-axis. So dx is the way we want to do the integral, right? Second, so you figure out dx or dy. With this particular shape, doing it dy, I would say no. I would just say like just hard pass. Because you'd have to figure out what the heck that cross-sectional shape is. And it's really not consistent, especially down here when you get like two of them. So yeah, hard pass on trying to do that as a dy integral. Good question though. All right, so we're doing dx. Next, second, figure out what's the range of values in x. So the region in the xy plane here just goes between x equals 0 and x equals pi. Right, that was the way I set that up there. So that determines our limits of integration. Now, what we need to do is just integrate the area of the cross sections. So what is the area of an individual cross section? So now we can kind of focus in on like one of these, right? What is the area of that? It's going to be like a triangle. So it's a half times base times height. If these are 45, 90, 45 triangles, you know, then they have base and base are like equal to each other, right? It's like a half of a square. So actually, instead of 1/2 base times height, it's simpler. It's just like 1/2 base squared in this example. And what is that base? Oh, all right. Issa has already put it in the chat. Issa's already answered that question. Yeah, there it is. Yeah. And Cheyenne's got it too. Yeah, it's the f of x minus g of x, right? The base of those triangles is the difference between those functions right there, right? So what were these? This was x plus 2, and this was sine of x. What am I doing here? It's kind of funny. Wow. Wow. I wrote x equals 2 over here, which is sort of silly because equals and plus are the same key on the keyboard. So like if I was typing this, that would be like an understandable typo, but I was writing it. Plus. I don't know how that happened. That was really weird. So we just put that in here. So it's going to be like 1/2 times the difference between those, top minus bottom. So like x plus 2 minus sine of x. And then that whole thing is squared. All right. So that's how we integrate it. 0 to pi. 1/2 x plus 2 minus sine x squared dx. How would you go about trying to solve that integral? What's your intuition? We could just plug it into Desmos and tell Desmos to figure it out. You know, we could do a numerical approach. We could just have Python, you know, add up rectangles. But what if you want an analytical approach? How would you solve that integral? Yeah, I agree. I agree with Cheyenne's suggestion in the chat there. You want to actually like square it, you know, distribute that whole squaring, get it like into 6 terms, right? And then just integrate each term. Some of them are going to be just x. Some of them are going to be like x times sine x. Some of them are going to be just a constant multiple of x. Some of them are going to be sine squared. But whether it's, you know, whether it's integrating sine or integrating x times sine or integrating sine squared, we have tools for all of these. You know, this is just easy Calc1, right? This one, how do you integrate x times sine x? By parts. Yep. By parts. So we can do that one. Yep. And what about this guy? How would you do sine squared? Yeah. Power reducing identity. That's right. And then I think followed by like a U sub. Power reducing and then a U substitution, if I remember rightly. So we can do that too. Right. So those techniques will all show up when you split that up and do that integral. So, all right. Have a good one, everybody. See you tomorrow.